Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 7 of a unit thermal properties of matter. So let's begin with today's class. In the previous classes we were discussing the radiation, and within the radiations we have discussed certain fundamental terms that are the radiating power, absorptive power, emissive power, emissivity, absorptions, and all that. As well as we have studied the Stephen Boltzmann's law. Now it's a time to study Wein's displacement law. So let's begin with Wein's displacement law. It says that the wavelength of maximum radiation is inversely proportional to the absolute temperature of black body. So this could be written as lambda would be inversely proportional to the 1 by t. It's a lambda minimum directly proportional to the 1 by t, or I should say it's a lambda into t. That is what it is equals to constant. This 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 could be written something like this, that lambda is equals to b by t, and this lambda m into t is equals to b. This is called as the Wein's displacement law, and this constant is Wein's displacement law constant, which value would be equals to 2.89 into 10 to the power minus of 3 m into k. Yes, it's a meter into Kelvin, that you understand. This is meter, this is Kelvin. So it is as simple as that lambda inversely proportional to the 1 by t. That's it, it is over. So at two different temperatures, let's say T1K and T2K of a black body, the wavelengths corresponding to maximum radiations, the wavelengths corresponding to maximum radiations are lambda 1 m and lambda 2 maximum are respectively. Then I could write it's lambda m1 into T1 is equals to lambda m2 into T2. That's it. I hope this is clear. Is it clear? Is it clear? Are you sure? Any doubts up till now? Is there anything? No? Great. So if I plot this graph, if I plot this, that this is lambda maximum versus temperature, this is look something like this. Yes. As soon as temperature increases, you can see that lambda m is decreases. Now one very, this is lambda m is equals to 1 by t. One very informative graph for this is the for the radiative power versus wavelength, based on this only, and that graph can be seen like this. Yes, so this is the maximum radiative power that we can receive, P max, and this is at particular wavelength lambda. Please do remember these things. Area of this graph is equals to sigma into t to the power 4, or I should say area of this graph is proportional to the t to the power 4. Please do remember this. Yes, this has been asked. I hope this is clear. Is it clear? Yes. So let's look at certain quick questions. It says that the wavelength of maximum radiation is inversely proportional to the absolute temperature. It's a lambda m, inversely proportional to the 1 by t. I hope this is clear. Next, a value of the constant in Wein's displacement law. It's a 2.9 into 10 to the power minus of 3 meter into Kelvin. I hope this is clear. So are you ready for the questions based on this? Great. Now let's look at this. Question is that if a certain body is at 727 degrees Celsius, can radiate a wavelength of 10,000 Armstrong. Find out its radiated wavelength. Find out its radiated wavelength when it is at 927 degrees Celsius. So what I'm supposed to do is first write down all the data that I've given. It's a T1 which is equals to 727 degrees Celsius. So I need to convert this. It is 727 plus 273. So this is 800 plus 200. This is equals to 1000 Kelvin. T2 which is equals to 927 degrees Celsius, which is 927 plus 273. It's a 1200 Kelvin. And wavelength 1 is given, this lambda 1 is given, which is equals to 1000. Keep it in Armstrong only. Lambda 2, that is what we want. So this can be written as lambda 1 into T1. This is equals to lambda 2 into T2. So this lambda 1, it's a 1000 Armstrong, 10 to the power 3 Armstrong, multiplied by temperature 1, it's a 1000 Kelvin. This is equals to lambda 2 that we don't know, multiplied by T2, which is equals to 12 into 10 to the power 2. So what I'm supposed to do is that lambda 2 is equals to, this is 10 to the power 3 into 10 to the power 2 into 10 to the power 1, divide by 12 into 10 to the power 2. This has gone, and this is 10 to the power 4 divided by 12 Armstrong. Yes, I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? Do you understand this? Great. Now, let's understood the one situation that according to the Boltzmann, according to the Boltzmann, or according to the Stephen Boltzmann, I should write this. The Stephen Boltzmann. This radiating power P was equals to E sigma A T to the power 4. Now, according to the Wien's displacement law, to the Wien's displacement law, this lambda is inversely proportional to the 1 by t, or I should say it's a t directly proportional to the 1 by lambda. So this could be written as power is directly proportional to the area divide by this t could be represented or replaced by the wavelength. So this is p directly proportional to the a divided by lambda to the power 4. I hope this is clear. Is it clear? Please keep this in mind because certain questions can be asked based on this. I hope this is clear. Is it clear? Great. Please note it down. Have you noted it? Have you? Great. Now let's work for the question. The question says that if two identical bodies designed from same material one of them radiates wavelength of 1000 Armstrong while other radiates wavelength of 1500 Armstrong. Find out ratio of their powers. This is requirement. How will you do this? First, let us right. What is given? They say two identical bodies. That means their radius would be equal, their area would be equal. Designed from same material. That means its emissivity would be equal. They radiate a wavelength of lambda 1. This is equals to 1000 Armstrong. It's 1000 into 10 to the power minus of 10. And the another one radiates a wavelength of 1500 into 10 to the power minus of 10. Now they are in meter. Find out the ratio of their powers. Yes, what I want P1 is to P2. So now let's do it. We understand that P is directly proportional to the A by lambda to the power 4. And when this is the situation, I should write it's a P1 by P2. This is equals to A1 by A2 multiplied by lambda 2 to the power 4 divided by lambda 1 to the power 4. As they said, A1 equals to A2. This 2 has been gone, and I have been left with lambda 2 divided by lambda 1 to the power 4. This is equals to P1 is to P2. So if I replace the data with the values, then I could have it's a P1 is to P2. That is equals to lambda 2. It's a 1500 to the power 4. 10 to the power minus 10 has been gone, and lambda 1 it's a 1000 into to the power 4. So this is basically a 15 to the power 4 divided by 10 to the power 4. I hope this is clear. This is the ratio of the P1 is to P2. I hope this is clear. Is it clear? Is it? Can you do this? Are you sure? So, do you understand completely what Wein's displacement law is all about? Are you sure? Are you sure? Yes? Great. Now, ready to move to the next topic, that is Newton's law of cooling. A very interesting topic, and we can relate this with our day-to-day life with very easily. So let's first understand what Newton's law of cooling is all about. According to the Newton's law of cooling, he says that the rate of cooling of a hot body is directly proportional to the mean excess of temperature of the body above that of the surroundings, provided that the difference in the temperature of the body and that of the surrounding is small. So he said that it's a rate of cooling which is d theta by dt is directly proportional to the T minus Ts, where T is the temperature, T is the temperature of body, while Ts, this is temperature, this is temperature of surrounding, this is temperature of the body, and Ts is the temperature of the surrounding. So, and this is what we call as the rate of cooling. This is rate of cooling. If I want to remove the proportionality constant, then I can add this minus of b. This is equals to d theta by dt, that is equals to minus of b into bracket t minus ts. So where I write this, t and ts are the temperatures of the body and the surroundings. B, this is a constant depending on the nature, shape and area of the cooling surface. And negative sign indicates that the loss of heat with the time. So this is the situation, and if this is the situation, I could write like this. It's a dq by dt. We have been known this Newton's law of cooling in terms of the rate of fall of temperature, dq by dt. This is rate of energy transfer. This dq by dt is equals to minus of b into bracket t minus ts, and as we know that dq is equals to m into s into d theta, so this is ms into d theta by dt, that is equals to minus of b into bracket t minus ts. So let's replace this value. It could be written as d theta by dt, that is equals to minus of b by ms into bracket t minus ts, and this could be d theta by dt, this is equals to k into bracket t minus ts, k into bracket t minus ts. This is just the rate of cooling. So here K should be is equals to minus of B by ms, and this is a constant. I hope this is clear. Yes. So this law can also be stated as the rate of fall of temperature. As it is a rate of cooling, it could be represented as a rate of fall of temperature of a hot body, and which is directly proportional to the mean excess of temperature of the body above surrounding. When I say mean excess, what it means? Let's understood. Let's suppose a body is going to cool uniformly from theta 1 to theta 2 and in time t. Then the average temperature of the body could be written as this theta mean or theta average could be written as it is equals to theta 1 plus theta 2 divided by 2, and this d theta by dt, it's a rate of cooling or rate of fall of temperature, could be written as theta 1 plus theta 2 by t. Yes. So according to the Newton's law of cooling, the situation was like this. It's a d theta by dt is equals to k into bracket theta minus theta s, and this could be written as theta 1 minus theta 2 by t, that is equals to k into bracket theta 1 plus theta 2 by 2 minus theta s. Yes, this is the approximation of the relation, but this will help to us. And when this will help to us, this can be used very easily. Yes, I hope this is clear. Is it clear? Are you sure? Are you sure? So basically, according to the Newton's law of cooling, it is d theta by dt directly proportional to the t minus ts. So we have derived the approximation form. We have derived the approximation form that said us that this is t1 minus t2 divided by t is equals to k. Here k is the proportionality constant. It's in k. This t is the average value. This is t1 plus t2 by 2 minus ts. It's a surrounding temperature. So even this formula can work very easily, and we are going to use this formula each time, every time. I hope this is clear. Is it clear? Is it clear? So please note it down this formulas. Please note it down this formulas, because we are going to use this, where T1 is the initial temperature. T1 is the initial temperature. T2, it is the final temperature. Ts, it is the surrounding temperature. This is surrounding temperature. I hope this is clear. And T is the time to reach from T1 to T2. So, so let's work for the Newton's law of cooling. Let's suppose the data is given something like this. If an object cools down from from 70 degrees Celsius to 60 degrees Celsius in 10 minutes, find out find out time required to cool it down from 60 degrees Celsius to 50 degrees Celsius. Surrounding temperature is 30 degrees Celsius, and assume Newton's law of cooling is valid. So this is the situation. How will you do this? what data they have provided to us. Let's work on this. So initially they said their initial temperature was 70 degrees Celsius. In this situation, their final temperature was 60 degrees Celsius. And to reach from 70 to 60, it took them 10 minutes. I hope this is clear. Now the situation is next time their initial temperature was 60 degrees Celsius. Their final temperature was 50 degrees Celsius. You want the time required to do this while surrounding temperature in both the case it's a 30 degrees Celsius. So please note it down the data and let's do the question. The situation was it's a T1 minus T2 by T. This is equals to K into bracket T1 plus T2 by 2 minus of T naught. So let's fit the data that initially it's a 70 minus 60 divided by 10 is equals to K into bracket 70 plus 60 by 2 minus T naught. This is equals to 30. Next, I am taking the ratio directly. This is the 60 minus of 50 divided by T is equals to K into bracket 60 plus 50 by 2 minus of 30 degree. So this is 70 minus 60, it's a 10 by 10 divided by 60 minus 50, it's a 10 divided by T. This is K and K has been gone. And this 70 plus 60, it's a 130 by 2, it's a 65 minus 30, it's a 35 divide by 60 plus 50, it's a 110, 102 10 by 2, it's a 55, and 55 minus 30, it's a 25. So this is the situation. This 10 has gone and this is 1. So this could be written as this is T by 10 is equals to 35, which is 7 into 5 divide by 25, it's a 5 into 5. This has gone, and this is 5 2s are 7 and this 5 2s are 10, sorry. This T is equals to 14 minutes. I hope this is clear. Is it clear? What was your answer? What was your answer? Was it same? Did you land on the same answer? Are you sure? Are you? Great. Well done. But is it clear up till now? Does it clear up till now? Are you sure? Are you sure? Great. So one thing that your mind must note it is that if you have not, please look at this very carefully. That from 70 to 60, you reach by within 10 minutes, and from 60 to 50 you took from 60 to 50 you took a 14 minutes. Yes, did you get this? Have you got this? Are you? That and in this situation surrounding temperature was 30 degrees Celsius. So if you want to reach from 50 to 40, it could be it could be greater than 14. I hope this is clear. You understand this. If 40 to let's say 31, let's suppose it could be greater than 14 minute, and let's suppose I call this time as a T3, then it is greater than T3 and at 30 degrees Celsius at infinite. So when you are going to touch exactly, when you are going to exactly match the surrounding, no, you are not at all going to match the surrounding perfectly. It is the situation. One more thing, why this happens, that this is we have proven because we have calculated it, and Once we have calculated it, we have proved it that this amount of time has been taken. And from this two observations, this is even correct. So why this happens? What is the reason behind this? What is the reason behind this? What I understand is that according to the Newton's law of cooling, what does it say? It says it's a d theta by dt directly proportional to the T minus Ts. So it means higher the difference, higher the rate of cooling. One more time, higher the difference, higher the rate of cooling. That means, look at this. Initially it was at 70, surrounding was at 30. So difference was a 40. Next time it was at 60, surrounding was at 30. So difference was 30. So in this situation, difference is higher, rate of cooling is higher. It's a 10 minute. But if it is 60 to 30, it is a rate is lower. Difference is lower, rate is lower. If you understood a 50 to 30, it is just the difference is 20 and the time taken would be much higher as compared to even in this situation. I hope this is clear. Is it clear? Is it? Do you understand this completely? Have you? Have you got this? Are you sure? Do you understand this completely? Are you sure? Can it be done? Can it be done? Are you sure? Great. So let's understood there are certain limitations too while using this Newton's law of cooling. Let's understood and let's discuss that. These are the limitations of law of cooling. So let's discuss it first. The surface of the body must be black to apply Newton's law of cooling. That's why I have written over there that assume that Newton's laws of cooling is valid. Yes. Next, the loss of heat must take place only through radiation process. The excess of temperature theta minus theta naught, the excess of temperature theta minus theta naught must not be large. It should be approximately 32 degrees Celsius to 35 degrees Celsius. Yes, this is the approximate measure that if this could be range, this can be applied. But most of the time when they are going to provide me a data, they itself they are going to write that assume that Newton's law of cooling is valid. And when they say that Newton's law of cooling is valid, you are definitely going to use this no matter what they have written. Yes, no matter what the difference is. Once a data provider tell me that Newton's law of cooling is valid, I am about to use it and there is nothing wrong in it. Next, the surface, that is what we call as the theta is equals to theta 1 plus theta 2 by 2, this must remain constant and this could not be vary. The air must be still. This all are the limitations, and once I understood this, I'm going to apply this. One more thing, a Newton's law of cooling is a very special case of the Stephen's law. So from the Stephen's law I can derive this. As you I'm much aware that you have gone through this derivation in your schools, so I'm not going to derive this, but this can be done very easily. Newton's law of cooling is applicable when the heat lost by conduction is negligible and the heat lost by the body is mainly by radiation, that we have discussed previously as well. And normally Newton's law holds good for small temperature differences up to 20 K or 20 degrees Celsius. This law holds good even for the large temperature difference in the case of the forced convection. So these are the certain limitations. These are the certain limitations of Newton's law of cooling. I hope this is clear. Is it? Now let's look at the certain quick questions. It says that Newton's law of cooling is a law connected with, yes, Newton's law of cooling is a law connected with, it is not connected with the convection, it is connected with the radiation. So conduction, no. Convection, yes, somehow, but that is specifically to the forced convection. But Mainly it represents the applications through a radiation. Next next a Newton's law of cooling. A Newton's law of cooling is a special case of, yes, it is a special case of Stephen Boltzmann's law. Next, next question. Newton's law of cooling holds good provided the temperature difference between the body and the surrounding is small. Yes, so approximation, exact data has not been provided that that should be 30 only or that should be 30, but some of the authors or majority of the authors written that it is approximately 30, because that can be easily verified on the practical life as well. So this is what we understood from the Newton's law of cooling, that it could be used when the temperature difference is small enough. Now, let's let's discuss some of the cooling curves. That means how the temperature is going to be dropped down and everything. So, it is the curve drawn between the temperature of a body and with respect to time. That is what we call as a cooling curves. So let's suppose on the y-axis I have taken a temperature, on the x-axis I have taken the time. So if I plot this y versus x, and let's suppose temperature is decreasing with respect to time as time is increasing. This can be plot something like this, and this is what we call as a cooling curve. I hope this is clear. Is it clear? So let's understood it. It's a curve between, it's this is the curve between the rate of cooling and temperature difference. So this is rate of cooling, which is directly proportional to the theta minus theta naught. This is Newton's law of cooling. It is something like this. You have remembered this. It's a d theta by dt. It's a directly proportional to the t minus t naught. So if I have taken rate of cooling, which is d theta by dt on the y-axis, and and difference of this surrounding, it's a t minus t naught on the x-axis. And if I plot this, this is a straight line. This is a straight line that passes from the origin. Please remember this. Now, a same situation, but now this rate of cooling, this d theta by dt, what we call as a rate, it's a this rate of cooling and log theta minus theta naught. Yes, I have taken the log on both the sides, and if I plot this, then this is again a straight line, that is for sure, but it is not going to be passed from the origin. It is basically something like this, that d theta by dt directly proportional to the t minus t naught. If I take this as a log of d theta by dt, let's call it log r, which is directly proportional to the log t minus of log t naught. I hope this is clear. And once this is the certain constant. That's why it is not going to be passed from the origin. Please do remember this. I hope this is clear. Is it clear? Is it clear? Let's look at certain quick questions too based on this cooling curves. It says that the curve between rate of cooling and temperature difference is a passing through the origin. It's a rate of cooling, that is d theta by dt, and temperature difference, it's a t minus t naught. Yes, it's a straight line. Next, the curve drawn between temperature of a body and time, that is what we call as the cooling curve. I hope this is clear. Is it clear? Do you have any doubts up till now? Is there anything? Do you have any doubts? Is there anything? No? Now, let's discuss the factors on which rate of cooling depends. It is the factors on which rate of cooling depends. This d theta by dt first depends on the t minus t naught. It is the temperature difference between object and surrounding. First, next, this d theta by dt depends on the area. It depends on the surface area. Higher the surface area, higher the rate of cooling. You might have experienced it as well, that higher the surface area, higher the rate of cooling. Next, d theta by dt, which is inversely proportional to the mass. If mass is higher, if mass of an object is higher, rate of cooling would be lower. Rate of cooling would be lower. Next, specific heat capacity, it's a d theta by dt, again 1 by c. If c is higher, this d theta by dt, this is lower. I hope this is clear. Is it clear? Is it? So these are the factors. These are the factor on which this depends. This cooling curves and this rate of cooling depends. I hope this is clear. Is it clear? Do you have any doubts up till now? Do you? Do you have any doubts? No? Great. Now, let's discuss some other graphs too. It is basically a graph from the conduction process. This is basically a graph from the conduction process. Let's look that this was the situation that uh, this is T1, this is T2, this was L, and this conductivity is K and something like this. So if I have been plotted a graph for this temperature versus length, that means from hotter end to the colder end, what would be the graph, how it would be? Let's first understood that road is this road is isolated from surrounding. So what happens? Let's assume that if it is at 100, next segment would be at 90, next segment would be at 80, next segment would be at 70, next segment would be at 60, and next segment would be at 50. It is something like this. I hope you understood this. Yes, so this could be plotted something like this. This is the highest temperature and this is the lowest temperature, but in this situation we have mentioned that road is isolated from the surrounding. When I have said road is isolated from the surrounding, I mean that only flow of energy is due to conduction on and radiation does not play any role. Radiation does not play any role in it. I hope this is clear. Yes, but let's suppose this cannot be achieved. Let's suppose this is the second case, that road is not isolated. Road is not isolated from the surroundings. Then what happens? If road is not being isolated, if road is not being isolated from the surrounding, then the situation would be, let's have a look. This is the temperature and this is the length. then it could not be a straight line, but it would be a curve, something like this. This is T1, higher temperature. This is the lower temperature. So in this situation, road is not isolated from the surrounding. So it means that if this was the road and this was at T1, this was at T2, then the through conduction energy will flow through this. But even radiation will be doing its part in this situation. I hope this is clear, and its temperature would be decreasing in a non-uniform way. I hope this is clear. Is it clear? Is it clear? Yes. Great. Now, I want to add one miscellaneous topic because it could not be differentiated. This is the part of this section only. That's why I kept it at the last, and that is the growth of ice on surface of lake. This is growth of ice on the surface of the lake. So when this will created, let's have a look that, let's suppose this is the lake and this is the upper layer, and this upper layer is generally at 0 degree Celsius, generally in most cases. Let's suppose this is the surrounding, and generally when and when we assume that ice is being formed, when we assume that ice is being formed, we understood that surrounding temperature is at minus theta degree Celsius, while the bottom of the lake is at approximately, this all are the approximate figures, is at 4 degrees Celsius. So when and when this surrounding temperature, when this surrounding temperature is minus theta, so by the time ice started to forming on the surface of the lake, but it is not going to be formed on the upper layer. No, this was not the case. I'm going to remove this. This was not the case. It is the ice is being formed from top layer to the bottom layer. So let's say this is the first layer that has been formed. Now if still the situation is same, that this is minus theta and still a very cold environment is there, then this is the second layer that is going to be formed. So from this top to bottom, from the top to bottom, this ice is going to formed. What amount of time will it take? That could be given by this formula. It's rho into L divided by 2k theta into bracket x2 square minus of x1 square. This rho, it's a density. Whether you take of ice or water, doesn't make any difference. L, it's a latent heat. Yes, from ice to water or water to ice, it's an 80 calorie per gram. K, conductivity of ice. This theta, it's a difference of theta naught, that is surrounding temperature, to 0 degrees Celsius. This is absolutely difference. And x2 and x1, this x2, it's a final thickness, it's a final thickness of ice, and x1 was the initial thickness of ice. Plus, please do remember this, that this is T is equals to rho L by 2k theta into bracket x2 square minus of x1 square. If I observe this very carefully, that generally this terms rho L 2k theta, this all will remain the same in most cases, and mostly whenever the questions has been asked, that questions has been based on this fact only, there is t directly proportional to the x2 square minus x1 square if all other parameters, are constant. I hope this is clear. Is it clear? Is it clear? Are you sure? So ready for the question? Have you noted it down? Please noted it down. Take your time and noted it down. This is one of the favorite questions of the examiners nowadays, that they need to certainly ask this question. Yes, if you have gone through the all the papers that have been asked in the JEE mains previous years, then in almost on alternate sessions, they have asked this questions. It's a growth of the ice on surface of a lake. So let's look at the question. Let's suppose the question says that if it takes 24 hours to form an ice of thickness 5 centimeter, find out time required, find out time required to form an ice of thickness from 5 centimeter to 10 centimeter. So this is the requirement, and you need to find out the time. How will you do this? What could be done? What could be done for this? What do you think? What do you think? How can you do this? So what I consider is that initially this x1 was 0 and this x2 was 5 centimeter, and in this situation the time taken was 24 hours. Now initially the x1 is 5 centimeter. In the second case x2 is 10 centimeter, and I need to find out the time taken. I hope this is clear. So let's call this as a 1, this as a 2, and I should write this, it's a t2 is to t1, this is equals to x2 square minus of x1 square divide by, this is the x2 square of x1 square. I hope you understand this is the first situation and this is the second situation. So x2 square it is equals to 10, it's a 10 square 100 minus it's a 5 square, it's a 25, divide by it's a 25 minus of 0, this t2 that I don't know, and t1 it's a 24 hours. So this 100 minus 25, it's a 75 by 25, and this is 25 3s are 75. So this is equals to t2 by 24. If this is the situation, this t2 is equals to 24 multiplied by 3. This is equals to 72 hours. This is the time. I hope this is clear. Is it? Do you have any questions based on this? No, this is one of the approach. One more thing, what you can observe is this is pretty good examples, that let's say it's in another approach of the same question. Let's understand that initially it was x equals to 0, then it will be x equals to 5, and time taken is, let's say, 24 hours. Now it would be an x is equals to 10. So if I assume that this is x, then this could be behave as a 2x. I hope this is clear. So if I consider it from x equals to 0 to x equals to 10, this is 2x, and if it is x equals to 0 to 5, it was x. So what I can understood is that let's call this as a first segment, this is the second segment, this is t1 is to t2, this is just the, I'm going to write the final option because it is initially both in both the section x equals to 0. So this is x1 square divided by x2 square. So this is x square divided by 4x square. This is equals to 1 by 4. And the T1 is of 24 hours divided by T2. So this T2 would be equals to 96 hours. But you must understand that this 96 hours is the time of this. It's a 96 hours of 2x from very beginning. So this time it's a 24 hours that we have written over here. So this 96 minus 24, this is the 72 hours. I hope this is clear. So basically this is this required time. Required time is 72 hours, that you understand. Basically this is a ratio of 1 is to 3 is to 5 is to 7 is to 9 is to 11 and onwards. Yes, that we have discussed this ratio. We have discussed this ratio in Galileo's law of odd numbers. Have you remembered this? Yes, it is the same ratio. It is the same ratio of the law of odd numbers, and this can be done easily. A very pretty, very good example. I hope this is clear. One more question that has been recently asked in one of the NEET examination was, let's look at this. They said that find out find out rate of growth of formation of ice. So we understand that this could be given as it's a rho L by 2k theta into bracket. Let's call it, it's a final, it's a x square. Now what I want, it is a very basic question. It is a rate of growth of formation of ice. So what you want? You want dx by dt, that is equals to what? So what I'm supposed to do is let's differentiate this on both the sides with respect to t. Then this will give me a d by dt of t. This is equals to d by dt of rho L by 2k theta into bracket x square. So all these terms are equal. All these terms are constant. Sorry. So this is equals to 1. This is equals to rho L by 2k theta into d by dt of x square. If this could be written as the 2k theta by rho into L is equals to d by dt of x square, which is 2x into dx by dt. This 2 could be gone, and this is growth, or I should say rate of growth. This is dx by dt. That could be written as this is k theta divided by rho into L into x. Yes, they have put up a certain data with this, and they frame a question, a very good question and very logical question, because we forget to write this is x dx by dt. That is where a problem is. I hope this is clear. Is it clear? Is it? Are you sure? So let's just wind up this session over here. This is all about the thermal properties of matter. This unit is complete over here, but please mind this, that this is having a very high probability. If you observe the NEET papers, then you will find at least two questions. This you will find at least two questions for the NEET papers. One of them belongs to the radiation, another of them, it belongs to the conduction. And if you are very good in your luck, then even one of the questions has been asked from the thermometry, that from thermometer or either from the calorimetry. So please do this. This will help us to get good numbers in no time. Yes, please practice a lot. This will help us a lot. Thank you. Have a good day. Take care. Bye bye.